Continuing on with the organic chemistry lecture series, we're going to move on to begin our discussion of Chapter 8, which focuses on alkynes. A lot of the reactions that we're going to see for alkynes are very similar to what we see in prior chapters, such as Chapter 7 for reactions of alkenes. Mechanistically, a lot of these reactions are going to be very, very similar. So first things first, let's talk a little bit about alkynes. What are alkynes? And in turn, how do we classify alkynes? So alkynes are hydrocarbons that contain carbon-carbon triple bonds. Alkynes fall into two major classifications, terminal versus internal. A terminal alkyne is at the end of a chain and it has an available carbon-hydrogen bond. Internal alkynes are placed in the middle of a chain and only contain carbon-carbon bonds at both ends. The formula of an alkyne is CnHn, and the Du value is 2 for an alkyne because there are 2 pi bonds. When we talk about alkyne nomenclature, you're going to name alkynes with the "-ine" suffix to indicate an alkyne. Just like with alkenes, the parent chain of the alkyne is the longest chain containing the alkyne. For example, the longest chain containing the alkyne in this case would be a 1, 2, 3, 4, 5, 6, 7 carbon chain. So this would be heptyne. Let's practice identifying the longest chain. So in this case, we count 1, 2, 3, 4. So this chain is the longest chain, and we need to have the longest chain including the alkyne. So we'll count down through the alkyne towards the longest chain. So we have a 6 carbon longest chain. So this would be hexyne. It would be a hexyne carbon chain. The full name, just for your reference, would be 3-ethyl. 1, 2, 3, 4, 5, 6. So it'd be 3-ethyl hexyne. More specifically, to denote the alkyne position, would be 3-ethyl 1-hexyne. For now, we just practiced identifying the longest chain. It's important to note you're going to number the chain such that the smallest locant number possible is assigned to the first carbon of the triple bond. So in this case, we'd count from left to right to give the triple bond a locant number of 2, rather than if we counted in the opposite direction, a locant number of 5. 2 is less than 5. We're going to count from left to right along this chain. So this would be 5,5,6 trimethyl 2-heptyne. That's the newer way of naming it. It can also be named 5,5,6 trimethyl hept 2-ine, which is the old school method of naming it. Both methods of naming are valid. Key point, the alkyne gets the lowest locant number possible. So for example, in this case, we have a choice between counting from left to right, or we can count from right to left. Comparing our locant numbers, we're going to prefer the locant numbers in red, counting from right to left, because we assign this alkyne to the smallest locant number, which is 2. So in this case, the full name of this molecule would be 5-methyl. This is a 6 carbon chain, so 5-methyl 2-hexyne. Now, what happens if you have multiple functional groups? So if double and triple bonds are at equivalent carbon locant numbers, the double bond is going to receive the lower carbon locant numbers. The double bond is a higher priority substituent when it comes to IUPAC naming. For example, the following compound would be named 1-heptane 6-ine, because we want to give the smallest locate number of 1 to the alkene if possible. This is compared to the alternative, where we assign a locate number of 1 to the alkyne. The alkene is higher priority, so it gets the lowest locate number. By the same token, if we look at the following molecule, in this case, we assign the lowest locate number of 1 to the alkyne because it is the lowest possible locate number. Just to be clear, there is no tie here, and as a result, we defer back to our original rule, which is to give the lowest locate number possible to either the alkene or the alkyne. You only give the alkene priority if there's a tie. So this molecule would be named as 4-methyl 7 known N 1 ine. So key points here. If there's a tie between an alkene and an alkyne, you give the alkene priority. If there's not a tie in locate numbers, you go with the lowest possible locate number for either the alkene or the alkyne, whichever one gives the lowest overall locate number. Okay, let's now talk a little bit about the preparation of alkynes. One common way that alkynes can be prepared is via elimination of vicinal 1,2-dihalides or geminal 1,2-dihalides. So here's an example of a vicinal dihalide, which has a 1,2 relationship. You have a halide at position 1 and 2. You can treat it with sodium amide, and that promotes elimination. Note, we have methods to prepare these dihalides. Dihalides can be prepared via halogenation of an alkene. So again, vicinal dihalides can be converted to alkynes via elimination via treatment with strong base, such as, for example, sodium amide. Alkynes can also be prepared via elimination of vinyl halides or geminal dihalides. So the geminal dihalide can undergo elimination to make a vinyl halide, and that vinyl halide undergoes a second elimination. This is why you need an incredibly strong base to generate the terminal alkyne, or an alkyne in general, depending on substitution. So let's try to apply what we've learned, and let's try to predict the product from the following reaction. So we're taking a vicinal 1,2-dihalide and treating it with sodium amide. What product would we expect to see? And let's draw each intermediate formed. So pause the video, work through this, and then we'll discuss. So the first thing that happens during elimination is that we eliminate one of our halides, either one, to generate a vinyl halide. Now, is this an E or Z vinyl halide? Doesn't matter. You have preference to make the E halide, but it's highly substrate dependent. Once you make our vinyl halide, the vinyl halide then undergoes a second elimination reaction, and that in turn generates our alkyne. Let's show how we can make alkynes from alkenes. So as discussed, we can treat an alkene with bromine followed by sodium amide, and that in turn allows us to prepare alkynes quickly and efficiently. To this end, let's fill in the product for each step in this reaction sequence. So I'll give you a few moments, pause the video, work through this example, and then we'll discuss. So in the first step, we're going to make the dibromide. This goes through a bromohydrin. Oh, sorry. This goes through a bromonium ion, and the bromonium ion gets opened up by the bromide anion to yield a 1,2 dibromide. Note that the two bromine atoms are on opposite faces of the molecule. From here, treatment with sodium amide facilitates quick and efficient elimination to generate the alkyne. Okay, let's keep going now, and let's talk a little bit about halogen addition to alkynes. So when you treat both an alkene or an alkyne with a halogen, you will get the trans dihalide. Unfortunately, in many cases, after the first equivalent of bromine or chlorine to generate this trans dihalide, the alkene that you make from this first step reacts a second time, and you often end up with a polyhalogenated product. It is very difficult to stop at the vinyl halide because this alkene is reactive enough to undergo further halogenation. So alkynes, when treated with one equivalent of halogen, will generate the trans 1,2 vinyl halide. Treatment with an additional equivalent of halogen yields this polyhalogenated product. The reason why it's so hard to stop at the vinyl halide is because under reaction conditions, you can't just drop in a single molecule of chlorine. You have a large number of molecules of chlorine floating around the reaction mixture, which in turn can further react with the vinyl halide product. Now, in terms of the mechanism for the reaction of alkynes with halogens such as bromine and chlorine, and the mechanism for alkyne dihalogenation, first and foremost, you end up with attack and cyclization to make a polonium ion-like intermediate. This ion intermediate is very strained, and it's not as easy to make as if you had this reaction involving an alkene. Nonetheless, this bridged ion intermediate can be attacked and opened from the opposite face, and that's why we get the trans 1,2 dihalide. This mechanism is very similar to the dihalogenation of alkenes, with the exception being instead of making an alkane 1,2 dihalide, if you use an alkyne as the starting material, you make a trans 1,2 vinyl dihalide. So let's try to apply what we've learned here, and let's try to predict the product for the following reaction, and I'd like you to draw a mechanism for each step in this reaction. So pause the video, take a few moments to work through this problem, and then we'll discuss. So first and foremost, the alkyne is going to react with our halogen, in this case bromine. We're going to generate a bridged ion intermediate. This is much more strained than your typical bromonium or halonium ion. From here, an equivalent of bromide will attack and open up this bridged ion intermediate, and that's why we get the trans 1,2-dihalide. So the two bromine atoms are going to be trans to one another because the attack occurs from the opposite face. From here, treatment of the resulting alkene with an additional equivalent of bromine, which is unfortunately stuck floating around in solution, yields this time an actual bromonium ion, which is then opened up by a second equivalent of bromide to in turn yield the polyhalogenated product. Why am I not putting stereochemistry? Because these are the carbons are not genuine stereocenters. They don't have four unique substituents. So if I had to give one summary of this dihalogenation of alkynes, you can try to use it to make vinyl 1,2-dihalides, but it's very difficult to control, and often you end up generating the polyhalogenated product. Let's talk now about acid-catalyzed hydrohalogenation of alkynes. So treatment of alkynes with halogen acids such as hydrochloric, hydrobromic, and hydroiodic acids will yield a vinyl halide. Further reaction yields the dihalide. So if you treat an alkyne with hydrochloric acid, you can make a vinyl chloride. An additional equivalent of hydrochloric acid yields the geminal dichloride. And we'll talk about why, in this case, you only observe the geminal dichloride. So in the mechanism, for the first equivalent, your alkyne is first protonated. This step is hard because this vinyl cation is not very stable. You're going to generate the most substituted carbocation still, because carbocations can be stabilized via substitution due to hyperconjugation. Your carbocation is then going to be attacked by an equivalent of chloride, and that yields your vinyl chloride. Now, unfortunately, this vinyl chloride can react with a second equivalent of hydrochloric acid, in which it's protonated. And in this case, you're almost always going to generate the carbocation at the carbon attached to the chlorine. Why? Because it's usually going to be the more substituted carbon, and this carbocation is resonance stabilized from the adjacent chlorine atom. So once you make your carbocation, which is the most stable, most substituted, and the resonance stabilized carbocation, it's going to be attacked by chloride, and you get the geminal dichloride. This is pretty useful because we haven't seen many methods so far to make geminal dichlorides. So in this case, I'd like you to predict the product for the following reaction and draw a mechanism. And in this case, I'd like you to stop at the geminal dihalide product. I'd like you to show both steps. Assume a complete full reaction to get the gem dihalide. So pause this video, work through this example, and then we'll discuss. So in this case, the first thing that's going to happen is we are going to protonate our alkyne. That in turn is going to generate the vinyl cation at the most substituted position. From here, the bromide ion is going to attack our carbocation, and that in turn generates our vinyl halide. Unfortunately, this vinyl halide is usually not going to be very long for this world, in that it will immediately be protonated, which in turn will generate a resonance stabilized, highly substituted carbocation, which is then attacked by a second equivalent of bromide ion, which in turn gives us the CHEM dibromide product. As you can see, this is the carbon that ends up here in the final molecule. Wonderful. So we're starting to see that there's a huge number of parallels between reactions of alkenes and alkynes. The mechanisms are almost functionally identical. The only problem when you deal with alkynes is you run into this issue of overreaction because you make an alkene and that alkene product can react further. Let's talk about radical hydrohalogenation of alkynes versus acid-catalyzed. So radical addition of HBr only occurs for HBr. If you're dealing with radical addition of and radical hydrohalogenation, only use hydrobromic acid for radical hydrohalogenation. The reason being has to do with the stability of the bromine radical and the fact that when you do radical reactions with the bromine radical, you get better control in terms of your product selectivity compared to chlorine or iodine. So radical addition of HBr to alkynes proceeds with anti-Markovnikov selectivity and mixed stereoselectivity. In other words, you get a mixture of E and Z isomers. Now, what's the mechanism? Well, as always, your peroxide is going to cleave to make an alkoxy radical, which can then abstract a hydrogen from HBr to make the bromine radical. From here, the bromine radical adds to the alkyne, and we generate a vinyl radical. That vinyl radical can then abstract a hydrogen and in turn we get the corresponding vinyl halide. Note the reason why the halogen ends up at the least substituted position is because it adds to generate the most substituted, most stable radical. Okay. So let's try to apply what we've learned and let's try to predict the products of the following reaction and draw a mechanism for this reaction. So pause the video, work through this example, and then we'll discuss. So first and foremost, let's just get the textbook initiation mechanism out of the way. The peroxide cleaves, you get your oxygen-centered radical. We abstract a hydrogen from hydrobromic acid to generate the bromine radical. And here we can actually start to do something. Once we have the bromine radical adds to the alkyne in order to generate the most substituted vinyl radical. From here, this vinyl radical abstracts a hydrogen from hydrobromic acid, which in turn propagates the chain and generates our vinyl halide product. Note we get a mixture of stereoisomers. Wonderful. Let's keep going now, and let's talk a little bit about alkene hydration. There are two methods of alkene and alkyne hydration, which are acid-catalyzed alkyne hydration and oxymercuration of alkynes. Let's talk about acid-catalyzed hydration of alkynes. Acid-catalyzed hydration of alkynes yields what's known as an enol. Commonly, even though you're working under acidic conditions, a source of mercury 2 plus ion is often used as a common catalyst. The way that this reaction works is fundamentally you have an addition of water into the alkyne to yield the Markovnikov product. This enol product tautomerizes via proton exchange with the solvent to yield a ketone. So the alkyne is hydrated, you get an enol. That enol then tautomerizes to yield a ketone. Let's talk about the mechanism. So for enol formation, first the alkyne gets protonated. You generate the most stable, most substituted carbocation. That carbocation is then attacked by water. And as a cleanup step, the protonated alcohol is then deprotonated to yield the enol. This enol readily tautomerizes to the more stable ketone. The way this occurs is via protonation of the enol carbon, followed by deprotonation of the carbonyl oxygen. This yields the ketone, which is the more stable tautomer. As a reminder, tautomers are interchangeable under acidic and basic conditions via a proton transfer. Let me draw these arrows more to scale. So whenever you get an enol, it will almost always tautomerize to the ketone, with some niche exceptions that we'll talk about later. So importantly, reaction of internal alkynes yields a mixture of ketones because both of these positions are equally substituted. And thus the carbocation that you make would be equally stable. Now, another method of alkyne hydration is oxymercuration. So when mercury 2 plus is used as a catalyst, carbocation formation is facilitated by the mercury 2 plus ion. So here you have coordination of the alkyne to mercury. You generate a carbocation. From here, that carbocation is attacked by water, and then you get a deprotonation step to generate the corresponding enol. That enol readily tautomerizes via a series of proton transfers. The only thing that's different when you have mercury as the catalyst is you will protonate the enol carbon-carbon double bond. And then from here, you get elimination of mercury to generate your final enol. This enol can then tautomerize to the corresponding ketone. So the key difference when you have mercury 2 plus, the alkyne attacks and coordinates to mercury, the carbocation's attacked by water. You protonate the enol carbon-carbon double bond, and you eliminate the mercury atom to generate your formal enol tautomer. That enol can then tautomerize to the ketone as normal. Just to show the carbon counts, if these are carbons 1 and 2, 1, 2, 1, 2, etc. I'm just marking these carbons to help you see the progression. So in essence, as a net result, we've installed a carbonyl at the most substituted carbon on the alkyne. So let's practice what we've learned and let's try to predict the product of the following reaction and draw the mechanism. And you can stop in this case drawing the enol, and you can just draw the ketone product from the enol if you prefer. So pause the video, work through this example, and then we'll discuss. So because we have mercury 2 plus, the alkyne will attack and coordinate to mercury 2 plus. That will in turn generate the most stable, most substituted vinyl cation, which then gets attacked by water. From here, we have some proton transfers to attend to, where first we deprotonate our alcohol. From here, we protonate our carbon-carbon double bond at the most nucleophilic carbon, which is the alpha carbon. And here we have elimination of the mercury ion. It could be water could help facilitate that elimination, but you can also just see elimination and loss of your mercury atom. And that in turn generates this enol product. And as we discussed, the enol can readily tautomerize to the corresponding ketone. Again, just to show mapping here, 1, 2, 1, 2. So in essence, we again installed a ketone, a carbonyl group, at the most substituted position. So this is the general mechanism for oxymercuration, and we talked about alkyne hydration under acid-catalyzed conditions. Let's talk about a method to prepare ketones and aldehydes at the least substituted position on the alkyne. To this end, let's talk about hydroboration-oxidation of alkynes. So hydroboration-oxidation of terminal alkynes yields aldehydes after tautomerization. This is very useful. The reason why this occurs is in hydroboration, borane adds to the least substituted carbon in an anti-Markovnikov fashion. So the alkyne undergoes hydroboration. You end up with boron installed at the least substitute position. After oxidation, you get an enol, which tautomerizes to an aldehyde. Let's talk about the mechanism. First and foremost, you observe concerted hydroboration. So you end up with addition of hydrogen and boron across the carbon-carbon triple bond. This yields a vinyl borane. Next, we end up with oxidation facilitated by hydrogen peroxide. The oxidation mechanism is exactly the same for prior hydroboration-oxidation reactions. And this yields a vinyl boronic ester, which is then hydrolyzed by hydroxide to yield an enolate. And because we already have this enolate we can show the protonation cleanup step in a single step where the enolate abstracts a hydrogen at carbon to yield our aldehyde. So as you can see, we've in net installed a carbonyl group at the least substituted position. Hydroboration-oxidation of alkynes is a wonderful way to prepare aldehydes efficiently. Let's practice what we've learned and let's redraw the mechanism once again. So as we discussed, we end up with addition of hydrogen and boron. In hydroboration oxidation, boron gets installed at the least substituted position. From here, hydrogen peroxide attacks our boron atom. That in turn yields the following intermediate. From here, we have an alkyl shift. Next, we have hydrolysis. And this is where we can save a step. So this is known as an enolate, and it is very reactive, very nucleophilic at carbon. So in this case, we can protonate not at oxygen, but instead at carbon. This in turn generates our aldehyde product. Quickly and efficiently. Let's just show some mapping here. 1, 2, 3. 1, 2, 3. So as you can see, hydroboration oxidation is a wonderful and efficient method to prepare aldehydes from alkynes. So we have two complementary methods to install a carbonyl at the most substituted position via oxymercuration or at the least substituted position via hydroboration. Really powerful stuff. Let's make this idea explicit and let's talk about applying alkyne reactions to prepare ketones and aldehydes. So using hydroboration and alkyne hydration, alkynes can be converted to ketones and aldehydes. If you want the ketone, you deal with oxymercuration or acid-catalyzed hydration. If you want the aldehyde, you do hydroboration oxidation. To make sure that you're clear on how to apply these reactions, I'd like you to provide the reagents needed to complete the following reactions. So we have two reactions, and I want you to give me two sets of reagents. So please pause the video, work through this example, and then we'll discuss. So in this case, we are preparing an aldehyde. So because we want to prepare an aldehyde, and we want to install the aldehyde at the least substituted position, we're going to employ hydroboration oxidation. In the second case, we are preparing a ketone, and the carbonyl is being installed at the more substituted position. So in this case, we're going to apply acid-catalyzed hydration conditions. This is really oxymercuration, but oftentimes for alkynes, because they're so unreactive, you often have to use a mercury catalyst anyway and be working under acidic conditions in order for this oxymercuration reaction to go with any level of efficiency. The last thing we're going to talk about in the context of generating ketones and carbonyls from alkynes is an introduction to retrosynthesis. So in this case, I'd like you to draw the alkyne used to generate the following ketone. So pause the video, think a little bit about what alkyne we could use to make this ketone selectively, and then we'll discuss momentarily. So in this case, we want to install this ketone at the most substituted position. So there are two possible ideas. The first of which is this alkyne. Let me just show the mapping here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We can also do the following alkyne. Of these two choices, I'm going to select the alkyne on the bottom. Why? Well, in this case, if we look at our two positions, we can very clearly get selectivity for the most substituted position. If we have this internal alkyne, both positions are equally substituted, so we won't be able to get any regio control. So we can prepare this ketone from this alkyne. Again, just to show the mapping, 1, 2, 3, 4, 5, and we're good to go. Because remember, oxymercuration can install a ketone at the most substituted position on an alkyne. So we can prepare this ketone from the corresponding alkyne. We pick this alkyne because we can get selectivity for one site over the other. We can get regioselectivity. Let's talk next about the oxidative cleavage of alkynes and reduction of alkynes. So in terms of oxidative cleavage, strong oxidizing agents such as ozone or potassium permanganate can cleave internal alkynes, producing two carboxylic acids. Terminal alkynes are oxidized to a carboxylic acid and carbon dioxide. In practice, these reactions are incredibly messy, and it's higher yielding to reduce the alkyne to the alkene before doing ozonolysis. So if I had to give you the better route, take the alkyne, reduce it, get the alkene, and then from here, once you have the alkene, then you can treat it with ozone, and that just works nicer. You end up with less byproducts. It's easier to isolate the products. It's very, very rare to see in modern synthesis for people to try this kind of direct, somewhat strongly oxidizing conditions to cleave an alkyne directly. Usually the alkyne gets reduced and then cleaved via ozonolysis. Now, in terms of the reduction of alkynes, hydrogenation is one of the more standard methods. Addition of hydrogen, facilitated with a metal catalyst such as palladium on carbon, converts alkynes to alkanes. So if you don't pacify or poison your catalyst, you'll reduce the alkyne all the way down to the alkane. In practice, alkynes can be reduced with a poisoned catalyst, such as the Lindlar catalyst, and that in turn allows us to convert the alkyne to an alkene. Hydrogenation using the Lindlar catalyst is particularly useful because it selectively yields the cis alkene. So this reduction is stereoselective. We only get the cis alkene from the hydrogenation with Lindlar's catalyst of an alkyne. So, to this end, let's predict the product of the following reaction. We have an alkyne. We're treating it with hydrogen and the Lindlar catalyst, which is a poisoned or pacified catalyst. That in turn, we'd expect to observe the cis alkene. In this case, this is the Z alkene. Really useful stuff. This is the first example that we've seen in this chapter of a highly stereoselective reaction. Now, in terms of reduction of alkynes, there's another way to reduce alkynes to get a transalkene. Alkynes can be reduced to transalkenes via dissolving metal reduction, which entails the use of sodium or lithium in liquid ammonia. If you've ever seen a video of this reaction, you may want to look up a video of a dissolving metal reduction, in that this mixture of reagents, lithium and sodium are very, very efficient reducing agents. And in this solution, you can think of it almost as if you have a pool of dissolved electrons. And in dissolving metal reduction, you can very efficiently reduce alkynes and other groups down. And dissolving metal reduction allows you to generate alkene products with a defined selectivity for the trans alkene. We will see further examples and applications of dissolving metal reductions. I would just like you to know that you really should remember these conditions, as these conditions can be used not just for the reduction of alkynes, but for the reduction of other functional groups. So what's the mechanism? First, you have a single electron reduction where lithium donates an electron onto the alkyne. Here we generate an anion. That anion, well, more specifically, a radical anion. That anion then pulls off a proton. You then get a second one electron reduction to generate another anion, which abstracts a second hydrogen via deprotonation, and this yields the trans alkene. So as you can see in dissolving metal reduction, we have a transfer of an electron, protonation of the anion, transfer of another electron, and protonation of the newly formed anion. The reason why dissolving metal reduction favors generation of the transalkene is in part because you're trying to minimize steric hindrance and steric strain between your bulky alkyl groups. So in this case, I'd like you to predict the products of the following reaction and draw a mechanism for this reaction. So we're treating an alkyne with sodium and liquid ammonia. These are textbook dissolving metal conditions. So let's pause the video. I'd like you to work through this example and then we'll discuss. So, as always, sodium, reducing agent, single electron reducing agent. We end up with donation of an electron that in turn generates this radical anion. The anion is protonated. Notice how the first step is a 1-electron process. The second step is a 2-electron process. Very important for you to keep that in mind. From here, I'm going to draw this like so. From here, we end up with sodium donating a second electron from a second equivalent of sodium. That in turn generates an anion. And that anion is then protonated. And with that, we get the corresponding trans alkene. And in this case, we have the E-alkene product. So we have two complementary methods once again to make a cis versus a trans alkene. Hydrogenation with Lindlar's catalyst gives us the cis alkene. Dissolving metal reduction gives us the trans alkene. This is very useful because we can combine what we've learned in this chapter with what we've learned in chapter 7. We can make alkenes with the defined stereochemistry and then react them in further stereospecific reactions to make products with defined stereochemistry. So, if you were wondering back in chapter 7, how do I get an alkene with a defined stereochemistry? This is one of the best methods to do that we've learned so far. Reduction of an alkyne can allow you to make an alkene with a defined stereochemistry, which can then be used in further reactions, as we'll see. So, with hydrogenation and dissolving metal reduction, alkynes can be converted to cis and trans alkenes, which can then be converted to other functional groups with stereospecificity. So we can take this garden variety alkyne and go all the way to alcohols with defined stereochemistry because we can make an alkene and that alkene can be converted to, in this case, a diol with stereospecificity. So net, we can take an alkyne and make a diol with defined stereochemistry. This is incredibly powerful. And this is why we teach chapters 7 and 8 together, because you can combine these methods to take an alkyne and convert it to these highly complex structures in a defined and in controlled manner. So let's do some practice now, and let's fill in the reagents required to complete the following transformations. So I'm going to do the first one, and you'll do the second one. And we'll think about what's going on here for each of the steps. Okay, so I'm taking an alkyne, and I want to make a Z alkene. This is done via hydrogen using hydrogenation with hydrogen and Lindlar's catalyst. From here, I want to install a diol with syn selectivity. And if I want to install a diol with syn selectivity, that's done via osmium tetraoxide, followed by sodium hydrogen sulfite and water. So osmium catalyzed dihydroxylation. Okay. Now that you've seen this first example, let's tackle this second example. And I'm going to give you a warning here that when we look at this next step, I'm going to rewrite and redraw this product in a way that's going to make it a little easier for you to see what's going on. One other way to draw this product that may be thought-provoking is that this product, if redrawn another way, looks like this. So what we can recognize is to go from here to here, we don't need syn dihydroxylation, we need anti-dihydroxylation. So you're going to need to be very cognizant of the conditions needed to prepare this diol via anti-dihydroxylation. With this hint in mind, you may want to pause the video, work through this example, and then we'll discuss. As you can see, overall, we're trying to find two unique methods to prepare the same product with a defined stereochemistry. Okay, so first and foremost, we see we're making an E-alkene. This is done via dissolving metal reduction. So lithium and ammonia. That gives us our E-alkene. One of the methods that we discussed to make an anti-dihydroxylation product is epoxidation plus ring opening. This combination, as we discussed in chapter 7, yields a trans 1,2-diol. There are a few other methods I could think of to give a trans 1,2-diol, but epoxidation ring opening is one of the more common methods. So in this case, what we're going to do is we're going to treat it with MCPBA. That's going to make the epoxide. And then we're going to open the epoxide with H3O plus and water. Just to show you what's happening here, we are making an epoxide. And then that epoxide is protonated and opened up with water. That in turn gives us, let's show the opening on this side just to make it easier. Both sides are equally substituted, but this more closely maps onto the product. So as you can see, we prepared the following product, which is directly equivalent to our desired product. So as you can see, combining reduction of alkynes with reaction of alkenes lets us prepare very complex molecules in a defined stereochemical manner. Very powerful stuff. Now, one other feature of alkynes is the fact that alkynes are acidic. Terminal alkynes are weak Bronsted acids with a pK of around 25. Thus, reaction of strong bases with a terminal alkyne produces an acetylide ion. Now, the acetylide ion is a powerful nucleophile that can react with electrophilic alkyl halides. For example, we can take one hexyne, we can deprotonate it with a strong base such as sodium amide, generate an acetylide ion, and if you have a carbon attached to a leaving group such as a halide, the acetylide ion can attack and displace the halide and thus we can form a carbon-carbon bond. So as you can see, we took one hexyne, deprotonated it, reacted it with this alkyl halide, and we formed this new carbon-carbon bond. So the acetylide ion is a really useful tool, is it's one of the tools that we've discussed now that allows us to form carbon-carbon bonds. So a terminal alkyne can be prepared via alkylation of acetylene, while an internal alkyne can be prepared by further alkylation of a terminal alkyne. So because acetylene has two available hydrogens, we can deprotonate, install one group, deprotonate again, and install a second group. So we can generate highly substituted alkynes with two unique groups through formation and alkylation of the acetylide ion. So what's the mechanism? Well, this is a textbook SN2 mechanism. The acetylide ion attacks the carbon attached to the leaving group, which is our halide, and the leaving group, which is the halide, leaves. So this is a concerted single-step mechanism. Carbon attacks the carbon attached to the leaving group, and the leaving group leaves. So let's try to apply what we've learned, and I'd like you to predict the product from the following reaction and draw a mechanism. So pause the video, take a few moments, and then we'll discuss. Okay, so first and foremost, we're going to deprotonate the acidic alkyne proton, and that's going to make the acetylide anion. From here, methyl iodide, which is our electrophile, is going to get attacked at the electrophilic carbon, which is the carbon attached to the iodine, and the leaving group is going to leave. This in turn forms our desired carbon-carbon bond. So just to be clear, this methyl group came from methyl iodide. Wonderful. Now, before you get ahead of yourself, the reaction of acetylide anions does have some very important limitations. These reactions are only efficient with primary alkyl bromides, iodides, and chlorides. Reactions with secondary alkyl halides gives elimination, converted the alkyl halide to an alkene. So let's make sure that we're understanding this limitation and we understand when we can apply alkylation of acetylide ions. And I'd like you to predict the product of the following reaction. So we take this alkyne, we treat it with sodium amide and then ethyl iodide, which for reference looks like this. So in this case, first and foremost, we are going to deprotonate and generate the acetylide ion. Because we have a primary alkyl halide, this reaction is going to work just fine. And we can in turn form this carbon-carbon bond with loss of our leaving group and generate the following alkyne. Let's now show how we can make a complicated polysubstituted alkyne. So I'd like you to indicate the reagents needed to accomplish the following transformations. So you're going to tell me the reagents to take this alkyne and convert it to this alkyne below. One hint is if you break these two carbon-carbon bonds, you can now have a hint of what alkyl halides to use. To demonstrate that point, I'll do the first case. So I'm going to label this A and B. If I break this bond, one way I could form this carbon-carbon bond is by using, if this is a CH3 group, methyl iodide. And to deprotonate my alkyne, I'm going to use sodium amide. If I break this, the acetylide ion I'd need to use would be derived from the following alkyne. So again, whenever you're picking apart an alkyne via these alkylation reactions, break the carbon-carbon bond attached to the alkyne, identify what group is going to be your alkyl halide, and identify what the acetylide ion is going to look like. So with that example in mind, let's try to draw how we'd prepare, and let's try to draw and show how you would prepare this alkyne. So pause the video, think about that for a few moments, and then we'll discuss. So just like before, I'm going to break this bond. This gets us back to an acetylide ion that looks like this, and an alkyl halide that looks like this. So I can use this alkyl halide. It's close to being problematic, but it's still primary, so we're okay. Let me just make sure. 1, 2. Let me just make sure my carbon counts are correct. So here we have 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. The halide needs to be here on carbon 3. Okay, and then to make the acetylide ion, I'm going to use sodium amide. So in a forward sense, I check and everything works out. Everything looks good. So as you can see, we can use polyalkylation of alkynes to prepare complex polysubstituted alkynes. Really powerful stuff. What we're now going to introduce to you is an overarching theory behind how to design and plan the synthesis of organic molecules. So this is known as retrosynthesis, and this is probably one of the most important concepts for success in the later half of this course and in Chem 113. So what is retrosynthesis? Well, if you're asked to generate a product from a given reactant, the first thing that I like to do is to recall and think about reactions and transformations that you are familiar with. Starting from your product, you're going to draw a reactant that can react to yield your product in a single step. From the new reactant, repeat this process of drawing a reactant that can yield your product in one step. Once you have drawn the intermediate reactants from your starting material to your product, fill in the reagents needed to complete each reaction step. This is what's known as rudimentary retrosynthesis. So for example, if I wanted to take this alkyne and convert it to this complex alkene, what I'm going to do is work backwards. Well, where can I make this alkene from? Well, this is an E-alkene, and I know I can make alkenes from alkynes via some sort of hydrogenation. Now, how do I get this substituted alkyne? Well, I can make this carbon-carbon bond via some sort of alkylation. And I can make this second carbon-carbon bond via some sort of alkylation. So now that I've traced things back and I've worked things back from my reactant all the way to the product, now I write out my steps in a forward sense. So I can make this first intermediate via alkylation of acetylene. I can install the methyl group via a second alkylation. And then I can make the E-alkene via dissolving metal reduction. So in retrosynthesis, You work backwards from your product to your starting material in single steps. Where can I get this product from? I can get it from here. Where can I get this product from? I can get it from here. And you repeat that process until you trace your way back to your reactant. Once you have traced all the way from your product to the reactant, you draw the forward route where you fill in the reagents necessary to complete each transformation. Now, let's talk about some formal terms in retrosynthesis. We have the general idea of retrosynthesis, where you work backwards from product to reactant. Now, there are some tools and named tools in retrosynthetic planning. The first of which is a functional group interconversion known as an FGI, where you convert one functional group to another. An example would be that I can convert and make an alkane from an alkyne via hydrogenation. The next type of formal step is bond forming, bond breaking steps. In this case, you can break bonds to generate what are known as retrons. So what is a retron? A retron is a fragment with a defined structure and charge. Now, you can't buy a retron in a bottle, but we can take these retrons and convert them into synthons, which are structures with the desired nucleophilic or electrophilic character. For example, if I wanted a carbon fragment where I have an alkyne with a negative charge in the alkyne carbon, well, this is just an acetylide ion. And I know I can make that from an alkyne. By the same token, a carbon with a electrophilic character at this carbon would be made from an alkyl halide because the alkyl halide carbon is electrophilic. You may find that one set of retrons gives synthons that are easier to make and that look more reasonable. So if I wanted to form this carbon-carbon bond and I have these retrons, I can make these retrons using the acetylide ion and an alkyl halide. And that's how we're going to do this synthesis. I can make this product by taking my reactant, treating it with sodium amide, followed by ethyl iodide. The reason why I like drawing out retrons before I draw out a formal structure for a synthon is that the more you learn in this class, the more possible structures you can draw with that specific electrophilic or nucleophilic character. For example, this retron can match an alkyl iodide, an alkyl bromide, a tosylate, a mesylate. There are a whole bevy of compounds and structures that correspond to this retron. Now, what synthon do we choose? Well, that depends on what synthon is easiest for us to get our hands on. We choose a synthon over another if it makes planning of the synthesis easier. So let's try to practice what we've learned, and let's try to indicate the reagents needed to accomplish the following transformation. And I would strongly encourage you to start with and to focus on approaching these problems from a retrosynthetic perspective. It's much easier to work backwards and then draw the forward route. So to this end, I'm going to do this first example. I'm going to show you how I would approach this using the retrosynthesis tools that we've learned. So first and foremost, I'm going to identify that these two bromine atoms are anti to one another. So I can make this dibromide via dibromination. And I can make this dibromide from an alkene. So I can make this exact dibromide via dibromination of this alkene. Now, this is an E alkene, and I can get that via dissolving metal reduction of the corresponding alkyne. Now, I can make this alkyne and I can trace it back to my starting material by breaking this bond. This gives us the acetylide ion derived from the starting material and a retron that looks like this. Well, I can make this retron just using ethyl iodide, the corresponding alkyl halide. Okay, so now that I've traced back to my starting material, let's list my conditions. First, I'm going to deprotonate the alkyne, and then I'm going to treat it with ethyl iodide. This in turn generates the following alkyne. To make my needed E-alkene, I'm going to treat with sodium and ammonia, dissolving metal reduction conditions, which in turn yield the E-alkene. From here, I'm going to treat this E-alkene with bromine, and that in turn generates the anti-1,2-dibromide. Perfect. So as you can see, by working backwards retrosynthetically, it allows you to organize your thoughts and approach the preparation of a molecule over multiple steps in a systematic and controlled manner. Let's have you approach this next problem, and I'd like you to tell me the reagents needed to accomplish the following transformation. I'm going to put some carbon labels down just for your reference here. And I'm going to rearrange these carbon labels to prompt and to give you a bit of a hint. So pause the video, work through this example, and then we'll discuss momentarily. Okay, so first and foremost, thinking retrosynthetically, I can make this alcohol very easily via oxymercuration or hydroboration-oxidation. So I'm going to make this alcohol from the corresponding alkene. Now, I could just have easily used this alkene. The reason why I'm preferring this alkene is it more closely resembles my starting material. And I can make an alkene from the corresponding alkyne. Well, there we go. So, in the forward sense, I'm going to reduce this alkyne with Lindlar's catalyst. You can also do dissolving metal reduction. This is a terminal alkyne after all. From here, if I want to place the alcohol at the more substituted position, I can just employ oxymercuration. So mercury acetate Let me make sure my conditions are accurate. Mercury acetate and water for the first step, and then sodium borohydride for the second step. That in turn yields an alcohol at the most substituted position, which directly matches the product that we were requested to prepare. Perfect. Let's do some more practice, and let's do some more advanced examples. So here I'd like you to indicate the reagents needed to accomplish the following transformation. And I'm going to give you a warning on this one. Do not try to make a vinyl anion and alkylate that. Just don't. So from here, I would again suggest approaching it retrosynthetically. Pause the video at this time, and then we'll discuss. Okay, so retrosynthetically, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Okay, so this is the new bond that we're forming. We don't have a lot of good methods to form carbon-carbon bonds from alkenes directly. So what I'm going to do is I'm going to derive this Z alkene from the corresponding alkyne. From here, this alkyne can be prepared via alkylation. And of course, how do we make this alkyne? Well, let's draw out our formal reagents. Well, one way that we can prepare alkynes that we've discussed is from the corresponding dihalide. And how do we get a dihalide? Well, we can make the dihalide from the corresponding alkene. Now let's go in a forward sense. So first things first, I'm going to treat this alkene with bromine. That in turn generates the dihalide. I treat this dihalide with sodium amide. That in turn eliminates the dihalide. From here, we can alkylate it via treatment with sodium amide, followed by ethyl iodide. That in turn generates the following. And from here, to make the Z-alkene, we do hydrogen with Lindlar's catalyst. Wonderful. As you can see, retrosynthesis is incredibly useful in that it allows you to see ideas and possibilities for your synthesis that would be difficult to recognize if you were just looking at the starting material and the product. By approaching synthesis in a step-by-step manner, working back from your product to your starting material, you can very easily plan an efficient multi-step synthesis. Wonderful. So that concludes our discussion of alkynes. We'll be moving on to discuss chapter 9, which focuses on substitution and elimination reactions.